Today we're going to talk about the graphical inverse of a function. And we know that an inverse basically undoes what a function does. So if I had the function f of x equals x plus 4, and I had the numbers negative 2, negative 2, negative 1, 0, 1, and 2, what does f do? Well, it adds 4. So negative 2 plus 4 is 2, 3, 4, and 0. Okay? 4, holy cow. How come my brain turns off every time you guys come in the class? There we go. Okay. What does F inverse do? Well, it does the exact opposite. If I had 2, 3, 4, 5, and 6, then that's going to be connected to negative 2, negative 1, 0, 1, and 2. Right? What would the equation of f of negative x be? It would be x minus 4. Now, if you ever want to know if two functions are inverses, you could test every single number. So plug in negative 2. Negative 2 plus 4 is 2, and I get 2. Now check that number in the other equation. Plug in 2. 2 minus 4 is negative 2. Did that bring me back to where I started? Yes. How long would it take us to check all the numbers? You never would be able to, right? They're an infinite number of points, so you would never test them all. So what you do is you plug this in here, and I get x minus 4 plus 4. What does that equal? X. Are those inverses? Yes, because when I combined them, I ended up with the function y equals x, which doesn't do anything. All right, graphically, what does that look like? Wait a minute. It's not x minus, is it x minus 4? Yeah, it is. So, on a graph, what does an inverse look like? Well, first, we have to know if a function is invertible or not. Okay? And in order to be invertible, it has to be a function, and it has to be one-to-one. Okay? So, is this function invertible? No. Why not? It fails the horizontal line test. Okay? Is this invertible? No, because it fails the vertical line test. It's not a function. Okay? What about an x to the third graph? It's a function. It passes the horizontal line test or the vertical line test, and it's one-to-one because it passes the vertical line test. And let's look at some of these numbers. This is y equals x to the third. And if I made a table of x's and y's, negative 2, negative 1, 0, 1, and 2, what happens when I plug negative 2 into this graph? I get negative 8. So negative 1, negative 2, and I get this point, negative 2, comma, negative 8. Okay? And then I could just go down the list, negative 1, 0, 1, and 8. Okay? Well, the inverse function is going to do exactly the opposite. Negative 8 gets sent to negative 2, 1 gets sent to negative 1, 0, 0, 1, 1, and 8, and 2. Okay? So I have this green graph where we graph the point negative 2, negative 8. But on my function inverse graph, I graph the point negative 8, 2. And I don't really have room for that. Let me move this over. Okay, so now I graph the point -8, -2 right here. Okay, on the green graph, -1. Oh, it should be -1, -1. And then this one should be -1, 1. Okay, so -1, -1 doesn't move. Okay, and then 0, 0 is in the same place, and then 1, 1's in the same place, and then 2, 8, which is somewhere up here, turns into 8, 2 right there. Oh, 2. That was a 1. So I get a graph that looks like this. And something really interesting happens. If I were to draw a 45-degree line, and hold on. Okay, look at that. Every point on the line didn't move. And then any point that was not on the line, if I connect it to where it went, those two lines are the same length. And the same thing happens over here. This one is equal to that one, which makes sense because all we've done is switch the x value for the y value. So why do the ones on the line not change? How come -1, -1, 0, 0, and 1, 1 didn't move? What happens when you switch 0, 0? It's still 0, 0. Guess what the equation of that line is? What's the equation of a line that has slope 1 and y-intercept 0? Y equals x, which is the identity function. Okay? So what happens on an inverse is everything on the line stays on the line, and everything not on the line jumps to the other side of the line. So if I had this, oops, that's not a very good graph. So if I had a square root graph that looked like that, and I wanted to invert it, I would have to draw the line y equals x, and then any point on the line stays there. So this point right here doesn't move. Okay? If you pick any other point, like this one, draw a line straight to the line y equals x, so that it's at a right angle, and then reflect that point over it. So this point is going to reflect to here. This point is going to reflect to here. This point is going to reflect to here, and here, and here, and this one jumps over there, and I get this graph. And if you kind of tilt your head sideways a little bit, you can see that I'm not a very good artist, but if you fold those two pieces together, they're identical. That's what an inverse graph looks like. So in your book, look at number 30. Did we not do that yesterday? Oh, oops. What's the assignment today? 19 to 27. Oh, wonderful. I'm teaching you the wrong one. I guess we're doing shoot. How did I? Hold on a second. Hold on. Oh, this is part of the assignment, right? Okay, sorry. Wow. Okay, so number 30. we need to draw that 45-degree line, and then 3 comma 1 gets turned into what? If I invert it and I switch the x's and y's, it turns into 1 comma 3. And you'll notice that this line and this line are the same length. Oops, that's a 4. Sorry, right here. Okay, so this one goes to there. Negative 3, 3 turns into 3, negative 3. And then I can connect those 2 points. And notice, see how those are the same? And if I fold the graph along that line, they meet. So we'll go back and do 19 through 27 in just a minute. Okay. What about number 32? And this is part of your set. So number 32. Okay. Yes, it's always the 45-degree line that hits 0, 0 up to the right. Every time. Because that is the y equals x function. Okay? So try to think of it as a reflection. This large piece on the right, this piece right here, if I reflect it over, it's going to go, this point's going to go here, and we're going to meet right there. Sorry, right there. And it's going to go, can you see how the reflection is going to work? So this point needs to go out here, and it's going to go like this. And that's the reflection. Okay. Well, on the first set, it wants you to graph them to verify that they are inverses, and then graph them. So let's do number 20 together. Number 20 says, f of x is x minus 2 over 3, and f inverse of x is 3x plus 2. And it says verify that f inverse of f is x. And then the other way, I just do one of them. It doesn't matter which one it is. So let's say I plug this in here. So it used to be x minus 2 over 3. And I'm going to put 3x minus plus 2 in there. And 2 minus 2 is 0. Or, yeah, 0. And I get 3x over 3, which is x. Okay. And then you need to graph it. So turn on your calculators and just type both of those functions in. So 3x, 3x plus 2, and then x minus 2 with parentheses around it. Oh boy. Divided by 3. Holy cow. What am I doing, guys? And then it's also a good idea to graph the line y equals x. And then you'll be able to see if they are in fact inverses. So here's my first line. Here's my second line. And then the line y equals x should run right down the middle of those. And then you would draw those graphs on your paper. Yeah, so you have to verify that when you compose them you get x, and then when you graph them that line y equals x runs right down the middle. No. Nope. Just draw a rough graph. I wouldn't even label the y and x axes. Okay, get to work.